Let us look at some theorems related to conjugate transpose of a matrix. First one, if A and B are matrices of the same order, then the conjugate transpose of a sum is equal to the sum of the conjugate transposes. Now, instead of writing it as A plus B, the whole star, we split it. So instead of writing it as conjugate transpose, let's split it into conjugate and transpose. Now, based on the property of conjugates, we have conjugate of A plus B is equal to conjugate of A plus conjugate of B, and transpose as it is. Now, based on the transpose property, we have conjugate of A plus conjugate of B, the whole transpose, is equal to the transpose of conjugate of A plus transpose of conjugate of B. And this can be written as A star plus B star. So we have conjugate transpose of A plus B is equal to conjugate transpose of A plus conjugate transpose of B, which is equal to the right hand side. Second one, if A and B are two matrices conformable for multiplication, conformable basically means that their orders are such that we can multiply, then A times B star is equal to B star times A star. That is, the conjugate transpose of a product is equal to the reversal in the reverse order. That is, conjugate transpose of B times conjugate transpose of A. This is also called the reversal law for transpose conjugate. So we have left hand side A times B star, which can be written in this form. Now, based on the property of conjugates, conjugate of A times B is equal to conjugate of A times conjugate of B, and based on the property of transposes, we can take the transpose to each of these matrices. So we have conjugate transpose of B times conjugate transpose of A, which means B star times A star. So we have A times B star is equal to B star times A star. So in general, by repeated application, we can get it like this. A times B times C times D dot 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 K times L star is equal to, in the reverse order, L star times K star times dot 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 D star times C star times B star times A star. Third one, the diagonal elements of a Hermitian matrix are necessarily real. So given A is equal to an M by M matrix, which is Hermitian, implies A sub ij is equal to the conjugate of A sub ji for all ij, such that 1 is less than or equal to I and j is less than or equal to m. For diagonal elements, naturally, I will be equal to j. So aii is equal to the conjugate of aii. So let a sub ii be equal to alpha plus I beta, where alpha and beta are in real numbers. Then the conjugate of a sub ii is equal to alpha minus I beta. So a sub ii is equal to conjugate of a sub ii implies a sub ii minus conjugate of a sub ii equal to 0. So substituting, we get alpha plus I beta minus alpha minus I beta equal to 0. Opening up the brackets, alphas cancel out, and we are left with 2I beta equal to 0, which means beta is equal to 0. So if beta is equal to 0, that means the imaginary part has disappeared. So hence, A sub I is in real numbers for all I. The fourth one, every square matrix can be uniquely expressed as the sum of a Hermitian and a skew Hermitian matrix. Given a square matrix A of order m by m, let's split it into two, half A plus half A, adding and subtracting half of A star. So we are adding half A star minus half A star. Regrouping, we get half of A plus half of A star plus half of A minus half of A star. What is common? So let's take it out. So half of A plus A star plus half of A minus A star. Let P be equal to half of A plus A star and Q is equal to half of A minus A star. Now let's take the conjugate transpose of P equal to half of A plus A star the whole star, which is equal to half of A star plus A star star, which is equal to half of A plus A star the whole star, which is equal to half of A star plus A, which implies P star is equal to P. And this is a bit tricky, so take it carefully and make sure you understand each step. So P star equal to P. Now let's take Q star, that is conjugate transpose of Q. So Q star is equal to half of A minus A star star, which is equal to half of A star minus A star star, which is equal to half of A star minus A, which is equal to minus half of A minus A star, which implies Q star is equal to minus Q. So do you notice what is happening here? The conjugate transpose of P is equal to P. That means that it is a Hermitian, and here in this case we have Q star equal to minus Q. So which means that Q is a skew Hermitian matrix. So that means A is equal to, coming back here, A is equal to, this is equal to P, this is equal to Q. So which implies A is equal to half of A plus A star plus half of A minus A star, where P is Hermitian matrix and Q is skew Hermitian matrix. So we have shown that every square matrix can be uniquely expressed. We have not proved uniquely, but we have shown every square matrix can be expressed as a sum of a Hermitian and a skew Hermitian matrix. But now we have to take care of the uniqueness. So let's do that. A is equal to P plus Q. Let A is equal to R plus S as well, where R is Hermitian and S is skew Hermitian. If R is Hermitian, that means R star is equal to R. And since S is skew Hermitian, it means S star is equal to minus S, which implies A star is equal to R plus S star, which is equal to R star plus S star, which is equal to R minus S. Because R star is equal to R and S star is equal to minus S. A plus A star is equal to R plus S plus R minus S, which is equal to 2R. Let's take it a little bit up, which implies R is equal to half of A plus A star, which is equal to P. Now let's take A minus A star. That would be equal to R plus S minus R minus S. That is R plus S minus R plus S, which is equal to 2S. S is equal to half of A minus A star, which is equal to Q. So what have we shown? that R is equal to P and S is equal to Q. But we started with the assumption that R and S are two other matrices, that is Hermitian and skew Hermitian matrices, whose sum is equal to A. But we ended up with the conclusion that they are nothing but P and Q. So R is equal to P and S equal to Q, which implies P and Q are unique. Thus, every square matrix can be uniquely expressed as the sum of a Hermitian and a skew Hermitian matrix. Now the fifth one. Every square matrix can be uniquely expressed as P plus IQ, where P and Q are Hermitian matrices. Given a square matrix A of order m by m, we have already seen A is equal to half of A plus A star plus half of A minus A star. So A is equal to half of A plus half of A plus half of A star minus half of A star. So A is equal to, let's rearrange this, half of A plus half of A star plus half of A minus half of A star. Half is common, so half of A plus A star plus half of A minus A star, but here we multiply it by I because we require I to appear. And the denominator I, we take it with 2. Let P be equal to half of A plus A star and Q be equal to 1 by 2i times A minus A star, so that A is equal to P plus IQ. Now P star, conjugate transpose of P will be half of A plus A star star, and following the same logic as in theorem 4, we end up with P star equal to P. So that means it is a Hermitian. P is Hermitian. Similarly, Q star is equal to 1 by 2i times A minus A star star. And following the same process, we end up with Q star is equal to Q. That means Q is also Hermitian. So we have A is equal to P plus IQ, where P and Q are Hermitian matrices. So we have shown every square matrix can be uniquely expressed as P plus IQ, where P and Q are Hermitian matrices. We have not shown the uniquely part of it. So now let's look at the uniqueness part. Let A is equal to R plus IS as well, where R and S are Hermitian matrices. So R star equal to R and S star equal to S, because they are Hermitian. Implies A star, that is conjugate transpose of A, is equal to conjugate transpose of R plus IS, which is equal to R star plus IS star, where we are taking the conjugate of I. So conjugate of I is minus I. So R minus IS. And now we take A plus A star, which is equal to R plus IS plus R minus IS, which is equal to 2R, which implies R is equal to half of A plus A star, which is equal to P, A minus A star, to take care of showing that Q is equal to S. So A minus A star is equal to R plus IS minus R minus IS, which is equal to R plus IS minus R plus IS. So S is equal to 1 by 2i times A minus A star, which is equal to Q. So again, S is also equal to Q. So R equal to P and S equal to Q, which implies we have unique P and Q. So every square matrix can be uniquely expressed as P plus IQ, where P and Q are Hermitian matrices. So that was conjugate transpose of a matrix, some theorems. That's it for now. Bye.